Jacobian for surface area element. And I wrote this thing in beautiful handwriting so that you will be like tempted to click in the thumbnail. I hope so. Yeah, okay. Let's proceed. Um, Usually this Jacobian thing is used in like volume element, right? So let's say if you wanna make a change of coordinates, right? And to go from one kind of volume element to another volume element, you use Jacobian, right? And in this video, I'm going to talk about how to use it for like surface area element. So first of all, I will actually do two examples. First of all, just finding volume of a sphere, right? And then which will be a familiar example. And after we are familiar with that, we'll also do example of finding surface area of a sphere. And this will not be the usual way you do it. This will be completely new. And I just discovered this like few hours ago, and like I was so happy and so excited, so I'm trying to share with him. Okay, so let's say you have a sphere, right? And you guys need to know about this spherical coordinate system first. Like, so if you have any sphere, so this is x, y, z. In the spherical coordinate system, you can parameterize this by a rho, which is basically the distance from the origin, right? And then angle theta, which is like how much is it's like uh the angle from x-axis, right? So if the projection of this line on the wait, this should have been okay. I think it's fine. I mean to say, okay, wait, let me redraw the figure the way I want to draw it. So I want to draw it like this actually: x, y, and z. Yeah. Okay, so let's say over here, and then there's this sphere, right? Over here. And yeah, okay, if there's a point, right, and it's on like a space, on a 3D space, and this is at some distance rho, and its projection on the xy plane is this line, right? So the angle from the x-axis of this projection is theta, and for this line, the angle from the z-axis, that angle is phi. Okay, so in spherical coordinate system, um, any point, like any point inside this sphere like can be located by these three coordinates, rho, theta, and phi, where rho can go from 0 to the radius of the sphere r, right? And theta can go from 0 to 2 pi, right? So 0 to 2 pi, this whole angle, theta can go from 0 to 2 pi, and phi can go from 0 to pi, right? So from here to up to here, 0 to pi. And yeah, so this is the parameterization, and like with this parameterization we can actually get any point on this sphere. Yeah, and you might want to check that like this point, this random point x, y, z, you can if you want to find that in terms of rho, theta, and phi, you can actually do that using simple trigonometry. X comes out to be rho sine phi cos theta. Y comes out to be rho sine phi sine theta, and z comes out to be rho cos phi. Okay, now that you know about spherical coordinate system, now we'll talk about how to find the volume. So basically, the volume of this sphere will be that this will be a triple integral, and like domain of the integration will just be like inside this sphere, right? So that means all the points that satisfy x square plus y square plus z square less than equals to capital R square, right? If R is the radius of the sphere, then yeah, all the points like that are in this domain. So that will be our domain of integration. Inside that, we just have to integrate dv, right? So this dv is just like dx, dy, dz, right? So we have to integrate that to get the volume, right? So now, okay, but the thing is, if you just try to integrate it like in Cartesian coordinate system, like using writing this as dx, dy, dz, the limits of integration will be too hard over here. Like this limits of integration will involve a lot of roots and things like that. But if we try to integrate this in like a spherical coordinate system, so like if we use that, then like the entire all the points on the sphere can be like written as like our rho going from 0 to r, theta going from 0 to 2 pi, and phi going from 0 to pi. On this domain, we actually reach all the points in the sphere, right? So now the domain of integration is actually easier. Now we just need to find out what this dx, dy, dz translates in this system of d rho, d theta, d phi in the system. Because this is not really dv, right? Because like dB was like small change in x, small change in y, small change in z. So that specific element, that is dB. So we have to find out like how you can get this same volume or dx, dy, dz using this d rho, d theta, d phi with something else in front of it. So that's what we have to find out, and we will substitute that thing over here. So how will you do that? That's the question, right? So the thing is, how you can do that is, you can basically first try to find out, like, okay, so how will like when you make like change in row, when you make a small change in row, how will like all these x, y, z coordinates change? Okay, so let me say how you find this out. So first of all, what you try to do is you try to find out how will this x vector uh okay, so this all this x, y, z change with row. So you'll try to find out, you'll try to find that vector. Yeah, so basically dx by d rho, dy by d rho, dz by d rho, right? So that will give you like how basically the small change in row, what kind of change it will create, right? Similarly, you can also try to find out how again this like x, y, z will change with respect to theta, right? So you will again have a vector. So dx by d, okay, now it's time for theta, d theta, dy by d theta, dy by partial theta, sorry, dz by partial theta, right? And then you can try to find out how these change x, y, z coordinates with respect to phi, right? Dx by d phi, dy by d phi, dz by d phi, right? Now, if you have that, if you now have that, like how like okay, so let's say by change in row, by small change in row, so this is the change that's created by small change in row, and like this is the change that's created by small change in theta, and this is the change that created by small change in phi. So if you have that, now you actually have like the amount of change in volume, because okay, so this is the amount of change in volume that is created by small change in rho, theta, and phi. That right? So you just need to find this volume now. And if you are able to find this volume, this volume, and after that you can just multiply by like this volume multiplied by d rho, d theta, d phi, right? Because this will actually be the rates in change. This will actually be like because these are all the rate of changes, right? So if you multiply by the actual rate of change, then only you get actual volume. So yeah, if you do that, then you get the change in like the actual change in volume, right? When there's a small change in rho theta phi. So that's what we will be you will be trying to do. And to find this volume, what I guess you already know that like let's say if you want to find the volume like of made by these three vectors, the parallelepiped made by these three vectors, right? So this is one vector, this is another vector, this is third vector, and like they make a parallelepiped here, and the volume of the parallelepiped will just be the determinant, right? So I just write all these three vectors as column vectors, right? And after that, I just take determinant, and that gives me the volume of the parallelepiped, right? So that's what I'm gonna do here. Dx by d phi, dy by d phi, dz by d phi. And if I take the determinant, so this is the volume of parallelepiped, right? And yeah, exactly. So our dV will exactly be this because this is because the rate, this will actually give a rate of change, right? So I have to multiply by d rho, d theta, d phi to get the actual change, and this is our dv. So you see, and this is exactly what it's called Jacobian. So Jacobian was clearly just like these three vectors, like how they made a parallel pipette, and we were just trying to find the volumes. These are like just the changes due to rho, due to theta, due to phi, and from those three vectors, we were trying to find the change in volume, which is smaller than rho, theta, and phi. So that's what we did, right? And if you just input like instead of dv, if you now just input this thing over there, now and then you can just calculate the volume, right? Okay, so now let's do that. That could be a little bit of like a difficult thing actually. But it's still okay. You guys can skip this part if it feels like a lot, but let me just do it for the sake of completion, right? Okay, now we will actually calculate determinant. X is rho sine phi cos theta. Y is rho sine phi sine theta. G is rho cos phi, right? Now the determinant will just be okay. Um, okay, dx by d rho is sine phi cos theta. Dy by d rho is sine phi sine theta. Dz by d rho is cos phi. Then dx by d theta is rho sine phi minus sine theta. Next is rho sine phi cos theta. Next is minus, okay, that's actually 0. The last one is rho cos phi cos theta, rho cos phi sine theta, and then this one is just minus rho sine phi. The determinant won't be too bad actually. I think I've done this earlier too. Sine phi cos theta, and this is negative rho square sine square phi cos theta. That's all interesting. Okay, and then plus rho sine phi sine theta minus rho sine square phi sine theta, and then minus rho cos square phi sine theta, and then plus rho cos phi cos theta. Right, let me check if the mic is on or not, because if that's the okay, yeah, good. Yeah, because when the video is going too good, I'm afraid if I'm even recording or not. Minus rho sine phi cos theta. Okay, so now this becomes minus rho square. This is actually sine q phi. I didn't expect that. Okay, am I doing everything right? No. I think I'm doing it right. Okay, I think it's going fine. It happens sometimes. Okay, minus rho square sine q phi cos square theta minus rho sine phi sine theta. And this one, if we take minus rho sine theta common, that will just go to 1 due to Pythagoras theorem. So this is multiplied by minus rho sine theta. Okay, and then this is minus rho square cos square phi cos square theta cosine phi. That's about okay. Now this is minus rho square sine cube phi cos square theta plus rho square sine square theta sine phi minus rho square cos square phi sine phi cos square theta. Okay, guys, what next can we do? Are we sure about the sign here? Okay, there was plus initially and then there's minus, so now this is a plus. Okay, so minus sounds out. Okay, so now over here, what can I do? Can I take sine? Okay, okay, that's actually interesting. Okay, what can I do? I can take Okay, over here between the first and third term, I can take minus rho square sine phi cos square theta common, and that gives me sine square phi plus cos square phi. That becomes 1, but the second term is still as it is, sine square theta sine phi. Now if I take minus rho square sine phi common, that goes to 1. Okay. Now this is this because this is a volume, right? So because this is volume, uh, because volume is a scalar quantity, right? I can actually make this positive. So this becomes rho square sine phi. Yeah, and this is actually a rate because all the thing here in the determinant are actually rate. So our dV, the change in volume, like the actual volume with units meter cube, like in Cartesian system, that thing, using this rho or theta phi will be rho square sine phi, and then d rho d theta d phi. Notice that here units match, like this is meter square, this is meter, so meter cube, right? So basically from here, this dV actually gives us the change in the actual, I mean the volume where the units is meter cube, like, yeah, I think good. Okay, now that we have dB, we can actually do the integral now. The integral is like rho going from 0 to r, theta going from 0 to 2 pi, and then over here now this thing phi going from 0 to pi of dv, and we know that this dv will be equals to rho square sine phi d rho d theta d phi, and this now becomes r cubed by 3. If you do sine phi, it's minus cos phi, and then 1 plus 1, that's 2, and then for theta, it's 2 pi. So it's 4 by 3 pi r cubed. So you get the volume formula, right? So this was just trailer, guys. Now only we are entering our actual content. So we see for volume, it was actually easy, right? So we just had to find out like what's the actual volume that's covered, like what volume is covered when there's a small change in theta, phi, and r, right? And then we found it, right? Now the approach will be same thing. Now approach will be same. Now, like to find the surface area, right, of this sphere, like, right? Now, like for surface area, our rho is constant, right? This is just r. The rho is just r. And now we need to find out like how when basically when this theta goes from 0 to 2 pi, and this rho goes from 0 to pi, right? This rho is basically the angle from g axis. This is rho, and the other thing is theta. So when like theta goes from 0 to 2 pi, rho goes from 0 to phi, and then phi goes from 0 to pi, and rho is just r. Like the whole surface area of the sphere is like covered, right? We can get any point by these three parameterizations, right? So yeah, so now we need to find out. So basically, when there's a small change in theta and a small change in phi, so what is the surface area that's covered over here, like on surface of the sphere? So that's why we need to find out, right? Again, the same thing. We first try to find out what is the change in like the coordinate, the change vector, when there's a small change in theta. So that's what we try to find out, and which we actually already find out, right? So basically, this was, you can write rho sine phi cos theta, rho sine phi sine theta, rho cos phi. So this was rho sine phi minus sine theta, and the next is rho sine phi cos theta, and next is minus rho sine phi. So this is the change created when there is a small change in theta, right? And now similarly, there's also change in phi. So the change created due to phi will be okay. So this will be a rho cos phi. I'm just tired of the simple derivatives. Okay, I'm sorry. Um, am I good? Oh wait, I actually did it wrong, guys. This one is 0. I'm sorry. Okay, that's 0 rho sine phi cos theta minus rho sine phi sin theta. Okay, and then rho cos phi cos theta, rho cos phi sin theta, and the last one is minus rho sine phi. Am I correct? Yeah. Okay, now that we had this, now again, what we want to find out is like, okay, so there's this small change like cos due to theta, right? So there's a vector, right? Due to, okay, so this vector is the change cos due to theta. This also change cos due to phi, right? In like this is in like 3D. There's change in x, y, z. There's also change in x, y, z. All of them. Now we just want to find out. So what is this surface area element? What is this surface area element which was caused due to change in theta and phi, right? So we just need to find out the area like made by the parallelogram of these two vectors, right? So again, what do? You just take these two column vectors and find the determinant, right? And that gives you, area. Same thing. Same thing, guys. Rho cos phi cos theta, rho cos phi sin theta minus rho sin phi. Yeah, now this is the determinant, right? And this will actually now, like, this is again a rate as I've been saying it, right? As I've been saying it, like these are all rates because this was like dx by d theta, this was dx y by d theta, dy by d theta, this was dz by d theta, this was dx by d phi, this was dy by d phi, this was dz by d phi, right? So this is like change caused in x, y, z due to theta and phi. But this is also the surface area element, right? This is also surface area element. And to get surface area, because this is a rate right now, we also need to multiply the change in theta and phi, right? D theta and d phi. So yeah, so we easily get surface area element, right? The only problem that you might be having on your head right now is that this is the rectangular matrix. And how do we find surface area, right? I mean, how do you find determinant, right? Because you cannot find determinant of rectangular matrix, blah, blah, blah. But wait, actually, there's a way. There's a way that how to do it. Like I also explained it in my previous video of like the art of messing around episode 2. You might want to check that out, right? For rectangular matrix, for M, if you want to find the area of the, okay, so let's say if it has k column vectors, right? So let's say if it has k column vectors, then like here we had like just two vectors, right? So we had to find area, right? So if there are k vectors, then it could be like k dimensional volume, right? K dimensional volume, depending on number of column vectors. So that k dimensional volume for a rectangular matrix, which we can also call as a determinant, we can find that out using the formula square root of determinant of M transpose M, right? And this actually gives you the and k dimensional volume, or like for this case, because there are two column vectors, two dimensional volume, which is area. So that's what we're gonna get, like area made by these two different vectors, the parallelogram made by them, right? So yeah, so and also you can see this formula as like, if you know that, I mean, it's not really a sensible thing, but if you just see that the determinant of these two matrices are equal if they are squared, even though they are not right now, and then if you see that, like you see that like both of them will have same volume and again square root, so it's basically like determinant of M itself. I mean, yeah, you can see it whatever you want, but this is the thing. And now, if you know that, you can actually take determinant, right? So this will be, and that's what I was talking about. This is the Jacobian, right? This is actually the Jacobian, the determinant of all these vectors. Like I forgot to write over here, but let me just write it. Let me just write it before I write this step. Let me bring this, and like, because over here previously also I wrote that vector right over here. So this was actually The this was I mean, didn't I write it? Okay, so this thing, okay, this matrix over here was actually row of xyz by row of, sorry, partial of rho theta phi, right? Similarly over here, the matrix for this is also rho x by, sorry, partial x by partial theta, partial y by partial theta, partial g by partial theta, partial x by partial phi, partial y by partial phi, partial g by partial phi. So that is the surface area Jacobian that I was talking about from the very beginning. The surface area Jacobian, right? So that's our title, Jacobian subset element. Okay, so that's what I was talking about from beginning, and yeah, we finally have it. And so yeah, so our DS is this thing. Now, okay, now let's do this. So first of all, we know that it should be the square root of the determinant of this product, right? So it's transpose. Don't worry, guys, that even though the terms looks heavy, I have already done this, and it's not as bad as it seems to be. Okay, so don't be afraid. But I do need a big space over here because this is a pretty big matrix, right? But it won't be that hard. Don't worry, guys. Don't worry. Determinant, right? And then there's this matrix. Now if you take the transpose, it will be minus rho sine phi sine theta, rho sine phi cos theta 0, rho cos phi cos theta, rho cos phi sine theta minus rho sine theta. I think I need to move this to this side a little bit. Maybe I should have done this a little bit smaller. Okay. And then now next one will just be, let me also move this a little bit. Let me extend this square root, right? Okay. Minus rho sine phi sine theta, rho cos phi cos theta, rho sine phi cos theta, rho cos phi sine theta 0 minus rho sine phi d theta d rho. Okay, now ds will be the square root of the determinant of the matrix we are gonna get in the determinant, right? And the determinant, right? And then d theta d rho. Okay, so this is going to be minus, okay, so this will be pretty easy actually. Minus, okay, this will be rho square sine square phi sine square theta added with rho square sine square phi cos square theta. So this is rho square sine square phi, right? The next one is minus rho square sine phi cos phi sine theta cos theta plus rho square sine phi cos phi theta cos theta plus 0. So that's a 0, right? Pretty easy. Next one, minus rho square sine phi cos phi sine theta cos theta plus rho square sine phi cos phi sine theta cos theta. So 0. And last one is 0. Last thing, rho square cos square phi cos square theta plus rho square cos square phi sine cos theta, which simplifies to rho square cos square phi, and then plus rho square sine square theta. Oh, wait. Let me do it again. Rho square cos square. Okay, I think this is sine phi. Okay, now it makes sense. Yeah, and if this is sine phi, this is also sine phi. And then in that case, now this is rho square cos square phi plus rho square sine square phi, which is rho square. So see, I told you it's not. It won't be that bad. Now this ds is the determinant of, this is just rho to the power 4 sine square theta d theta d rho. So d theta d phi. So ds is just rho square sine phi, and that's sine square rho square. I'm sorry, guys. So rho square sine phi d theta d phi, and that's exactly the subsidiary element that we wanted. Now it's so easy. Now, so yeah. Now this rho will just be fixed to be r, right, and all the theta and pi will be varying. So you will have theta going from 0 to 2 pi, phi going from 0 to pi of the surface area element, which is theta going from 0 to 2 pi, phi going from 0 to pi. And this is just r square sine phi d theta d phi r square. As it is for theta, it's 2 pi. For sine phi, it's minus cos pi, again 1 plus 1, which is 2. So it's 4 pi r square, and we get the surface area of a sphere, guys. So we now finally have both surface area, volume of a sphere, as well as surface area of a sphere, and this was so cool, guys. I just loved this because even I'm new to this. I just discovered actually this afternoon, and I was so excited to share with you all. You are my first to go friends. And yeah, so this is all about Jacobian subsidiary limit, and I think that you really learned something new, like how to do something like this. Like even though there are like three and then two variables, and then there's rectangular matrix, but you still try to find its determinant, right? The same interpretation like determinant, like even this thing as well as normal determinant of the square matrix both give n-dimensional volume. Over here this n is number of column vectors, over there the column and row are same, so actually both are have same interpretation. That's of the n-dimensional volume, right? So you can just say this as determinant instead of this some like gram matrix, something like that. You don't need to say that. And yeah, I think this was pretty cool. I definitely think this was pretty cool. And like this all, and like the interesting thing is, this can be generalized to any dimension. You don't need that cross product thing now. Like even if let's say there were, even if you let's say you wanted to find like k-dimensional surface area, you can still use this formula, right? So let's say in like you are in 10 dimension thing and you want to find this 9-dimensional surface area, you can still use this thing. Like if it's like 10 dimension and 10-dimensional volume, then you can just use normal Jacobian, right? But if it's like 10-dimensional like space and you have to find 9-dimensional surface area, you can use this idea, and this perfectly works, guys. Like the cross product thing only works in 3 dimension, but this one any dimension, and that's the beauty of it, guys. And I definitely believe you loved it. Personally, I did. And I think this was a lot to learn, and I think maths is beautiful. Okay, guys, that's it for today. I look forward to seeing you in like upcoming videos where I will come up with similar beautiful contents. I look forward to seeing you in the upcoming videos. Keep watching, keep sharing, keep learning, and keep having fun.